Very good. Then I think it's time to start with the introduction. So a warm welcome to the AIJA Exponent webinar on the current trends in the global liquefied natural gas industry. My name is Victoria Keri. I'm the Association Manager of AIJA, the International Association of Young Lawyers. The association has existed since 1962, that's almost 60 years, providing an outstanding learning and networking platform for lawyers under 45 from all over the globe. 2 years ago, we started our collaboration with Exponent, a leading international engineering, scientific and regulatory consulting firm present in the US, Asia and Europe. Their services and 50 years of expertise are very relevant for our members, and therefore we look forward to starting our first joint webinar. The webinar will be recorded and made available to AIJA participants and all the webinar participants later online. And we would also like to kindly ask you to fill in the online feedback survey that will be shared shortly after the call to help us improve. I'm now giving the floor to Myra from Exponent to introduce our esteemed speakers.
Well, thank you very much, Vicky, and the AIJA team. We're really happy to be a part of the webinar today, and just in general, happy to be a part of AIJA. So I'd like to introduce a couple of my colleagues who will be speaking today on the current trends in the global LNG industry. First colleague is Dr. Harry Kaitoma. He's a Group Vice President and Principal Engineer in the Exponent Boston office. He's a mechanical engineer and he's worked on numerous LNG projects in the US and internationally. He's served as a US representative to the ISO TC67 WG10 working group that developed guidance for the planning and design of onshore LNG facilities and associated marine activities. And before Harry worked at Exponent, he was actually a professor at MIT. Another speaker that we have is Patrick Lawson-Early. He's based out of our London office and fairly unique. Patrick is a master mariner and a manager in the London office. Extensive experience with LNG Marine Terminal construction, commissioning, and operations as a project marine advisor, marine terminal manager, and marine manager for LNG ship owners and operators. And then we also have, she's there in the office with Patrick, Maria, and she's a naval architect and manager in the London office as well. And she's extensive working experience in ship design, construction, plan approval, and regulatory compliance for shipbuilders, ship owners, and classification societies. We unfortunately weren't able to have Francesco Colella with us today, but his background is thermal engineering and sciences, and so hopefully he'll be able to join us for another webinar later. So that is our Exponent team of presenters. So if Harry, you'd like to take it away.
Absolutely. So thank you so much for the introduction.
LNG.
Can you hear me? I hope you can all hear me. So my name is Harry Kaitoma, as you heard, and I'll be kicking this off, and then Patrick and Maria will be speaking just after me. So again, thank you to AIJA for hosting us today. And allowing us to give this presentation. And what I'll be talking about really is the rather exciting activity that's going on globally with liquefied natural gas. So to kick us off, let me just address a simple question as to what liquefied natural gas is. So natural gas is typically 85% methane. It has high molecular weight constituents like ethane and so on. It's produced either directly from gas reservoirs or as an associated gas in the normal production of crude oil. So when crude oil is produced, there is also natural gas dissolved in it that is a byproduct of crude oil production. So methane is CH4. That's the molecular structure of methane. It has under normal conditions in the atmosphere here, it has half the density of air, and it becomes a liquid at a temperature of minus 160 degrees Celsius or minus 260 Fahrenheit. As a liquid, it's about half the density of water. So if you spill LNG on water, it'll float on water. And that's relevant from the standpoint of safety issues that one has to be concerned with. One of the great benefits, and that's really driving a lot of what's going on in the world, is that methane puts out on a per energy basis much less carbon dioxide, approximately half, for example, of what coal would put out, and also doesn't emit any sulfur dioxide, nor does it emit particulate materials when it is burned. So that, you know, these environmental advantages have been driving very strongly what's going on in China, and we'll get into that a little bit more. But specifically, there's a big push in the last 3 years under the Chinese Blue Sky Initiative to replace the combustion of coal with the combustion of gas, natural gas. But methane itself is actually a potent greenhouse gas. It's about 20 to 30 times more potent than carbon dioxide. And so when it is vented into the atmosphere, it's a problem. So the industry, while there are a great many environmental benefits associated with methane that I just described, venting or fugitive emissions associated with methane is going to be a sort of a great area of focus from a standpoint of ensuring let's say the environmental friendliness of the use of methane. Of course, methane is a fossil fuel, so the combustion of methane itself does produce some carbon dioxide, which continues to be a concern both from a policy standpoint and global warming potential. So, what does the infrastructure look like? The natural gas is produced either on land or offshore. So you can see in the far right an onshore production rig, as well as here, if you can see my cursor, an offshore production platform. The gas is produced, and then using pipelines, it is sent to a gas treatment facility. In the gas treatment facility, removes hydrogen sulfides, water, as well as natural gas liquids like ethane, propane, butane, and so on. And once the gas has been treated, it goes to a liquefaction facility that you see over here. The liquefaction facility is really a large refrigeration plant. I'll go into some detail about that a little bit later. The liquefied natural gas as a liquid is produced, it's stored in tanks, and then offloaded onto ships, and the ships go off to market, like, for example, to the regasification facility in the far left over here. Other exciting things that are happening in the industry, in fact, for the first time in 2019, we now have what are known as floating LNG or FPSO, floating production, storage, and offloading facilities, like the very large structure that you see over here. And these are, as the name suggests, floating facilities that do everything that an onshore facility does, but it does it offshore to monetize stranded resources offshore. And the way an FLNG facility operates is a ship will then come to the side of it and then transfer the LNG over to the ship, and the ship will go off to market. And so the production of LNG is done with these FLNG systems, very complex systems that are now emerging in the marketplace. There are also floating storage and regas units, and these have been around actually for a good 15 years. But what these are is facilities of ships typically that will store gas store LNG and allow the regasification of the LNG so that it can be introduced into the network of gas pipelines at the market end of things. And so you can see here the FSRU is connected to a pipeline that then delivers gas in the far left of this image. So where is all of this going on? So this is really a good graphic that summarizes the global situation today. And so the top 10 LNG exporters on the left rectangle in 2018 were Qatar and Australia. Now, what's interesting about this picture is that there's enormous activity right now in the United States, and Russia. And so what you're seeing really is a window into 2018. 2019 and the next few years ahead of us will actually begin to develop a different picture. The demand for LNG, or who is importing the LNG, in short, is Asia. And so you can see here, Japan, China, and Korea. The interesting picture associated with the import of LNG is that China is becoming a big player and only just recently overcame Korea. Korea is now in third place in 2018 as an importer. And what's going on in China and the aggressive development of the import infrastructure is really going to continue to change this picture, as you'll see. So if you look at liquefaction projects, so these are the export projects, and who is doing what, and I'll sort of focus your attention first on the right-hand side. You can see that there are really two major peaks. So this slide on the right shows you the export capacity that's coming online by year. And you can see that in the first peak over here, you have the light blue, so there's Qatar. So essentially the first decade of this millennium, Qatar developed a major infrastructure, and also Africa was coming online in red. Now, in this particular decade, the second decade of this millennium, the big activity that you're seeing is first Australia, then Russia and the US. And so that's what's happening right now. So if you look at where we are today, so we're in 2019 right here, and you can see that United States has got a lot of infrastructure coming online this year and next year. I'll show you that. And Australia is at the tail end of its major push in development. So if you look at the increment in 2018, just the increment in 2018 of the export capacity, you can see that Australia was the one that contributed the most, consistent with the prior chart, and then US and Russia contributed each around 8 million tons per year. Now, where are these facilities? So you can look at geographically where these are situated. So in Australia, here I'm showing all of the liquefaction projects. The two major projects in Australia are the Gorgon Chevron project and the Northwest Shelf, and each of these is approximately greater than, so around 15 million tons per annum, or MTPA. Prelude is actually the first floating liquefaction facility, and you see it over here. It came online this summer, delivering its first shipment in June 2019, and there are more FLNG projects on the horizon today. In the US, the picture is actually really quite interesting. This is, again, the capacity that's come online. And so you can see in 2019, there's a steep rise. And this year, we've seen, well, first in 2019, we've seen a continuation of the Sabine Pass trains, liquefaction trains. So the fifth one just came online about a year ago. And then you're seeing Corpus Christi, Cameron, Freeport coming online. And so really the picture that's emerging in the US is twofold. One, big push in 2019. 2020, next year, promises a very large number of projects, up to about 100 million tons per annum, going to final investment decisions, FID, which means that there's a potential for the liquefaction capacity in the US to actually double in the next 5 years or so. But you know, it's a very dynamic marketplace right now, so yet to be seen exactly how that transpires. Most of the projects in the US today, most of the capacity is in the Gulf of Mexico. You can see here Sabine Pass, Cameron, Freeport, Corpus Christi. There are projects worth mentioning that are developing right now on the West Coast. These are noteworthy because the greatest demand, as you saw, is in China or Asia in general, and the distance from the West Coast to Asia is considerably shorter, about 10 days shorter than from the Gulf of Mexico. I'll say a few words about that in a little bit. Also noteworthy is the fact that there are about, I'd say about half a dozen projects that make up the opportunity for doubling the North American capacity in the next 5 years or so. Now, Russia is interesting. Yamal LNG has been online now for a couple of years. What's unique about the two developing projects, the Yamal LNG and Arctic LNG in Russia, is that these are on the Arctic Ocean, and they demand or have required the development of more sophisticated LNG ships, specifically ones that have the ability to operate in ice and the ability to break ice. As I pointed out, that the greatest demand is in Asia. The demand is less in Europe, and so really right now the goal for these Russian projects is primarily to sail via the Russian Northern Sea route that you can see here through ice to the Asian market, and in the wintertime to cater to Europe. And economically, the greater demand market actually fetches a higher price. So there's a real drive for the Russian LNG to cater to the Asian market. So what does a liquefaction facility look like? The liquefaction facility from a technical standpoint is really a thermodynamic cycle that is similar in character to your refrigerator at home. So a refrigerator in your home has a compressor that compresses the refrigerant. And so that's the piece of equipment that actually sometimes makes some noise in your fridge at home. And in compressing the refrigerant, the refrigerant is heated up. And so the second important function of the refrigerator is to reject heat. And so in the back of your fridge, you've got these sort of coils that heat up and reject heat into your kitchen. And so a liquefaction facility has to have a large compression capacity, and that is done using compressors that are driven by gas turbines, or essentially modified aircraft engines. And the typical appearance of a liquefaction facility will reveal that you have a lot of heat exchangers to reject the heat that is created. The compressed and cooled gases then go through an expansion valve that causes the refrigerant to cool significantly. That then enters a heat exchanger. So in your fridge, that's the cold plate in the inside of your fridge. And at a liquefaction facility, that's called the cold box. And the cold box is really a sort of an important piece of technology associated with liquefaction terminals. And so the refrigerant then cools the gas, and the gas is brought down to a temperature of around minus 160 degrees Celsius, making it then a liquid. And the important point to note here is that the liquefaction technologies are really populated today by three major players. The most dominant that provides the entire cooling process is the Air Products C3MR. C3 stands for propane, and MR is mixed refrigerant. And the mixed refrigerant is actually made out of hydrocarbons, including things like ethane and propane. Other players in this liquefaction technology include the Preco. That's probably the oldest, and typically supplied by Black & Veatch, as well as the ConocoPhillips optimized cascade process. And so you're seeing those three in the marketplace, and there are new ones that are coming online as the world continues to develop this capacity. So here is a picture of the Prelude, floating liquefaction facility. And what's interesting about the Prelude is that well, first it's floating, so it operates offshore. And so the processes have to be able to accommodate wave actions and things like this that you do not experience onshore. And in essence, the facility or the platform has to accommodate all of the processes ranging from the production of the gas to treatment all the way to liquefaction in about a quarter of the footprint. So you can imagine a lot of the systems are packed very closely on this very large ship. The dimension of the ship is about 0.5 kilometer by 75 meters or so. So it's absolutely enormous. And you can expect to see more facilities like this developing in the next 5 to 10 years. Let me skip to China. So now I'm sort of swinging over to receiving terminals or regasification terminals. So in the last 3 years, there's been an enormous push in China to develop the import infrastructure to receive liquefaction, liquefied natural gas And the reason for this has been primarily to replace coal that has been a great source of pollution in China with natural gas, with its benefits associated with clean combustion. And so as a result, you've seen the three major national oil companies, and you can see here, CNOOC, CNPC, and Sinopec, essentially are really leading the charge. And the Chinese market is also opening up to non-national oil company import terminals that we're sort of seeing coming into play. And you can see these color-coded actually on this particular graph. The interesting thing about China is that not only are they developing an enormous import infrastructure, but they're also investing in the liquefaction capacity globally. So they have been, for example, minority investors in the Russian projects that I described to you. They are a player in the Canadian Canada LNG project, Shell's Canada LNG project, and others, including Australia. So really, China is a major player, and this is helping them secure the LNG supply, not just building the infrastructure to import. So regasification terminal, here's an image of a regasification terminal, is considerably simpler than a liquefaction facility. Essentially, the primary components of a regas terminal are the ability to accommodate the LNG carrier that you can see here, to offload the LNG into the tanks that you see, and then to vaporize them. Essentially, the vaporization involves adding heat to the liquid so that it is gasified and then injected into the network of pipelines. Another important point associated with the regasification is that each of these terminals will have a fairly tight specification regarding the heating value as described through what's called the WOBI index, to ensure that it satisfies the marketplace. And so it satisfies the required narrow range of combustion characteristics, for example, that are important in gas turbines that help generate power. And so for that, nitrogen is often introduced into the stream to make sure that the specs are met. Now, I mentioned earlier floating storage and regasification units, and so these really have been around for about 15 years, and what they are is primarily ships. In fact, many FSRUs are repurposed LNG ships, but they also have a regasification capacity, capability of regasifying the LNG. And these are either floating just offshore and connect to an infrastructure of gas distribution pipelines, or at a berth, as you can see, the white ship right here in the image on the right. LNG is actually a commodity that is considerably different from things like gasoline or crude oil or other fuels, in that it is stored at cryogenic temperatures, minus 160 degrees C, and it is stored in tanks, whether on shore or on ships. These tanks have to be insulated with fairly sophisticated insulation systems, and no insulation system is perfect in the sense that it will leak some heat into the tank, and so that results in what's called boil-off gas. And all LNG storage systems will have boil-off gas, and you have to have strategies to manage that. And what that means is that you cannot store LNG passively in a tank without having to release some methane into the atmosphere, if you were to do so. And as I mentioned before, methane actually is a potent greenhouse gas, and so for that reason and other economic reasons as well, you need to take sort of measures to ensure that something is done with the boil-off gas. And boil-off gas can be reliquefied; it can be used in engines, for example, on ships, as fuel. And as the shipping fleet increases in size, and the technology continues to develop, we're seeing now better and better insulation technologies on ships as well as on shore. And so you can see here that the boil-off gas rates in all ships is 0.25% per day. Modern ships are considerably lower than that. In fact, some are below 0.1% per day. So a few words about marine transportation. So here, this is a global map, and really the point that I wanted to make with this particular slide is to show you first that Australia is close to the greatest LNG market in Asia, as you can see. So it makes sense for projects to be located in Australia. The other major producer today is Qatar, right close to the Strait of Hormuz, and you can see that the distance to market, to Asia in particular, is a little bit longer. But then in contrast, with this enormous infrastructure that's developing in the US and in particular the Gulf of Mexico, the distance is actually much larger. And there are a couple of factors here. So obviously, just simply the geographical distance, but also the fact that the Panama Canal is a little bit of a bottleneck for the transportation of LNG from the Gulf of Mexico to Asia. And the standard route, the route is to go through the Panama Canal and then sail across the Pacific over to Asia. There's been a recent expansion of the Panama Canal, and so that now they can accommodate more than one ship per day. But as the LNG liquefaction capacity increases, we expect that will become more of a bottleneck than it is today. So looking at the global LNG fleet, the picture is really interesting. So here what I'm showing is a number of vessels coming into use by year. And you see the exact same picture that you saw in the liquefaction capacity. So you can see there are two humps, one hump in the first decade, another hump in the second decade. And these decisions associated with new builds are actually made typically in coordination with final investment decisions associated with export terminals. So it's no surprise that the two look very much the same. And here you can see in the first hump over here, you can see these green ships correspond to Qatari projects, so QFlex and QMax. And then the Russian projects, including the Yamal LNG that I pointed out earlier, has had the development of these icebreaker ships, and that show in orange in this second hump here. So actually, let me go back to that particular slide. So it's, based on this, you can see that about half of the population of the ships are less than 10 years old, and half of the population are probably more than 10 years old, just based on when these came on board, and that is reflected in this particular histogram. So here you can see the total fleet represented. The total fleet is about just over 500 vessels globally, and the ones that are less than 10 years old are mostly ones that can sail through the Panama Canal, so between 150 and 180,000 cubic meters in capacity, and the ones that are a little bit older than 10 years old. So these are the ones that show up in orange over here. These are the ones that were associated with the Qatari projects that are in operation today. So the interior of these ships looks simply fascinating. There are really two types of ships primarily that are in use today. 2/3 of the fleet of 500 or so have membrane tanks, like I show on the left over here, and about 1/3 are these Moss type tanks, and these differ considerably in their design and use of materials. Really, the biggest differences are that the Moss type is made out of one large aluminum or aluminium shell that ranges in thickness between 1 and 6 inches, so ranging from 2.5 centimeters to about 15 centimeters in thickness, while the membrane type is actually contained using a membrane that is of the order of 1.5 millimeters and then made out of stainless steel or 304 stainless steel. And the big design difference between membrane and Moss types is that the hull on the membrane type ships actually supports the weight of the LNG, so the weight is not supported by the membrane or the secondary membrane, but rather the forces are transmitted directly to the hull, while the Moss type sphere is actually self-supporting. It has its own structure, that supports the sphere. One of the sort of the interesting things that's going on in the industry today is that really over the last 2 decades, the leaders in the manufacturing of the fleet of LNG tankers that we have is primarily Korea, and really, and there are 3 major shipyards in Korea: so Daewoo, Hyundai, and Samsung Heavy Industries, and they today command the majority of the order book for new builds of over 100 ships approximately. And to put things in context for you, the cost of a new build is around 200 million, and the majority of these ships are membrane ships, and the technology associated with the membrane is owned by one company, GTT. And this is a French company called Gaz Transport Technigaz, and they charge approximately 5% of the cost of a ship to allow these shipyards to build and use, essentially purchase a license, and that's about $10 million a ship. And so the Koreans have had really for about a decade or so a very strong push to develop their own membrane technologies, and very recently there have been announcements from both Daewoo and Hyundai that I'm showing here to really showing approvals that the Korean shipyards are receiving for their own membrane technologies. And so I think an interesting space to watch is how the intellectual property associated with the membrane technology is going to develop in the near future. But I think it's safe to say, I mean, if you look at the order book for new builds, most of them today are still going with GTT, but there's a strong push from the Koreans to change that. So with that, let me pass the baton to my colleague Patrick, who's going to tell us about LNG Marine Terminals. So Patrick.
Okay, thank you very much, Harry. Taking it over here, the LNG Marine Terminal, as you can see in the picture, this is the interface between the ship and the shore. Basically the same for both liquefaction and regasification, and consists, the important thing with all the LNG Marine Terminals is that the ship and the terminal have to be compatible. So there are a number of industry guidelines, industry recommendations to ensure that the ship and the terminal match, and all the ships are constructed to match all the terminals. And an organization called SIGTO, the Society of International Gas Tanker and Terminal Operators, provides most of that regulatory information so that all the ships fit all the terminals. And also, of course, the marine terminal is part of a port, so there has to be other infrastructure. There have to be tugs, pilots, channels, traffic arrangements to ensure, or the LNG ship is not hindered when it's entering port. Things of this nature. So having an LNG terminal in a port can have quite an impact on the port operations. And the other alternative is ship-to-ship transfer of the LNG. This is where two ships will moor alongside each other offshore, transfer cargo one to the other. Originally, this was really an emergency procedure if a ship broke down or similar. But with the Arctic LNG projects that Harry was talking about earlier, it's now become quite normal. The new ice-breaking ships, although they're perfectly capable of trading worldwide, it's not economic. They don't have an efficient hull shape for long ocean voyages as they are icebreakers. So it is better from an economic and operational point of view to bring the ships out of the Arctic to a suitable location, bring a conventional LNG ship alongside and transfer the cargo for the conventional ship to take it off to market. The other reason is that the Arctic LNG fleet is quite small, and if the ship was off on a long voyage somewhere else, there wouldn't be a ship to load the next cargo. So the system is becoming quite routine now. There have been 83 STS operations on the Arctic project so far this year. So that's a fair number of cargoes. And the system will move further, particularly with small-scale LNG, which I will come to later, as that will often be a large ship transferring cargoes to several smaller ships. An LNG ship voyage is basically quite simple, but has some factors which are not normal, which are unique to LNG. The main one being that because the LNG is cryogenic, the cargo tanks must be cooled down before the cargo is loaded to at least minus 100 Celsius in order to avoid any problems when you start loading the liquid. And at a loading rate of 10,000 to 14,000 cubic meters per hour, that varies with the terminal and the ship, but it is usually within that range. The ship will be alongside for about 24 hours in port, loading period of 12 to 16 hours. And during that loading period, obviously, the tanks, when the ship arrives, will be full of natural gas from the last voyage, and loading the cargo, pouring liquid into a tank, will make that cargo circulate and will generate even further gas, which must go somewhere, and you can't vent that to atmosphere, as we've said previously, so it's returned to the terminal where it is handled by the various systems. During the voyage, there will again be some losses due to heat ingress, although the tanks are exceedingly well insulated, and as Harry said earlier, the technology's improved a lot over the years, but also the engines have become a lot more efficient, so there are less losses. But LNG is unique in that during the voyage, the ship consumes some of the cargo as fuel. This is calculated and taken into account in the commercial agreements and everything else, but is something that is slightly unique to LNG operations. And then you come to unloading at the regas terminal, which is the reverse of loading. The ship pumps the liquid ashore. The terminal provides gas back to the ship to replace the volume in the tanks on the ship. As you cannot have a vacuum in the tanks on the ship, this would place unacceptable stresses on the ship, but also may permit oxygen to enter the tanks, which could then create a flammable atmosphere and various other problems. On a conventional LNG ship, the ship will retain a small portion of the cargo at the end of unloading. This is to allow them to use some of the cargo, some of that small amount of cargo as fuel on the way back to the loading terminal, but also to enable them to have enough cryogenic liquid on the ship to cool the ship down prior to starting loading. The LNG ships will be chartered. Normally, a ship owner will place an order with a shipyard to construct a ship. As Harry said, a lot of these will be placed either as part of a project or more usually nowadays on the basis that the ship owner knows there's a lot of projects coming up and will start placing orders for ships so that he can then bid for long-term contracts from the companies which are planning to construct the new export terminals. A ship costs around about 190 million US, and charter rates are they average between $65,000 and $85,000 per day. So the ship owner should amortize his costs fairly quickly. As you can see from the illustration, the charter rates are very variable and fluctuate a lot. And in November 18, the end of 2018, there was a peak in charter rates. This was due to some of the new liquefaction, particularly the ones in the USA, coming on stream when the ships being constructed to serve them weren't all available, and thus obviously this introduced a premium, particularly as the US terminals are further from the market than some of the other terminals, and therefore you need more ships to service the same route. The rate then dropped off after that, as you can see, and since then has fluctuated. The summer of this year, the rate was around 50,000 per day. Currently, at the end of October, the latest charter rate I've seen was 130,000 per day. So as you can see, it's peaking again now, probably because of the Northern Hemisphere winter, and again, the fact that the number of ships required doesn't quite match the amount of demand in the market. Ships are chartered on either a time charter or a voyage charter. Time charter is a long-term charter, at least 5 years, ideally from an owner's point of view, 10 or 15. These are usually associated with the major projects and will be by the oil companies or large LNG trading concerns who will hire a ship for a long period at a fixed cost. So the charter rate will not vary. It will be set based on the market conditions at the time, and the charterer will try to get it as low as possible, and the owner would obviously like it as high as possible, and it will be based upon future trading and other such things. And in this case, the charterer is paying for everything. He pays for the ship, he pays for the fuel, he pays for the port charges. The only bit the owner pays is the crewing and the technical management and maintenance of the ship. So the charterer tells the ship where to load, where to unload, etc. For a voyage charter, this is a single voyage. The ship is hired purely to take a cargo from port A to port B, and these will usually be spot market cargoes. The LNG market is normally long-term agreements. When they need to finance a project, they will try to set up long-term sales agreements where a regas terminal will agree to take 20 cargoes a year, 50 cargoes a year, something similar, so that the owner, the charterer, the terminal, everybody knows what is happening, what the costs are, what the economics of the project are. But there are often fluctuations in markets, and some cargoes that were scheduled to be part of a long-term agreement won't be needed at their original source or their original market, and will be offered for sale on an open market. These sort of cargoes will end up being carried on a voyage chartered ship. And the ships that undertake voyage charters will normally be ships that are on a long-term charter to somebody, but are not needed at that particular time, so will be placed on the spot market in order to cover the costs while they are not employed on their primary role. And the cargoes are carried either as ex-ship cargoes or as free on board. Ex-ship is very simple. In fact, the two systems are. Ex-ship is normally for long-term agreements, as I've said, where it's 20 or 30 cargoes per year to a specific terminal, and the transfer of ownership of the cargo happens when the ship puts the cargo into the tanks at the regas terminal. With a free on board cargo, which is usually associated with voyage charters, the cargo is loaded onto the ship and then becomes the customer's cargo, and they can unload that wherever they can sell it. That's the difference between the two. And finally, LNG, as we've said, there are a large number of new liquefaction projects. China and other parts of the world are taking in more and more LNG to fuel natural gas because of its green credentials, if I can call it that. But also there is a lot of small scale LNG now, which is a new and increasing situation. The regulations for ships' fuel are changing in 2020, and there will be a cap on how much sulfur can be in ships' fuel. And a lot of owners are changing over or constructing new ships so that they can burn liquefied natural gas as a fuel on the ship. This is driving small-scale storage facilities, small ships to supply the larger ships with LNG, etc. And also LNG is being used as a fuel for trucks, for trains. It's being transported by train. There are many and myriad uses, and new containment systems, new small ships, etc. Thank you very much. That's all I have at the moment. I believe we have a little bit of time for questions for myself or Harry or anything else. If anybody has any questions, of course.
So we see a question here. So this is Harry speaking. From Eveline asking, are you familiar with faulty ISO containers, cargo tanks, and other types of containments leaking significant amounts of boil-off LNG? And so the, I mean, let me go first with this. I mean, you know, we've definitely, I mean, we've worked on a number of cryogenic containment systems that have failed in some fashion that prevents them from insulating the cargo, and the upshot of this is then sort of excessive boil-off gas. And there are different kinds of systems out there. And so, for example, some are insulated with, like, for example, if you look at the membrane system, that is a system, interestingly, that provides the insulation with polyurethane foam and plywood. That's what provides the insulation. In smaller systems, cryogenic tanks are insulated using a double barrier and a vacuum between these. And so you're seeing the range of technologies, and we've worked on both, systems that don't operate correctly on ships, where for some reason the insulation is not working, and there can be many reasons that have to do with both the gases within the insulation spaces, as well as how the insulation material, like the foam itself, is performing. And in vacuum insulated systems, like pipe-in-pipe vacuum insulated walls, or containers that have a vacuum between two barriers, that if you lose the vacuum, you can now cause essentially a significant loss of performance in the insulation related to convection between the two barriers that was supposed to be at a vacuum but no longer is. Patrick, anything else?
Yeah, agreeing with everything Harry says, and yes, ISO containers, small tanks, trucks, trains. I have seen faulty containers. They're unusual unless they're dropped or otherwise damaged, and the tank containers are fairly robust. But it is possible. It does happen. Most of the smaller scale tanks, like ISO containers, because there will be some heat ingress and transportation, it's calculated so that you have a certain amount of time to transfer the container. You can't keep it cold. It is insulated, usually by vacuum, as Harry said. And what will happen is the pressure in the container will gradually increase as the temperature of the liquid natural gas rises. The tank is pressure rated. If you store it for too long, or you put it in the wrong place, or you disturb it, or whatever else happens, it is possible for the relief valves to lift. It is also possible for those to be faulty, but it's not a common occurrence. It is definitely not. It's unusual and would not normally occur, provided the container is properly constructed and properly utilized and used according to the standards.
Harry and Patrick and Maria, thank you guys for joining us. Vicky and Georgia, thank you guys so much for helping us host. And yeah, thank you guys for joining. If you have any other questions, we'll send a follow-up link for the survey. And if you guys have any additional questions, I can direct you to Harry and Patrick directly. But thank you, everyone.